Okay, so this is a very short lesson actually, and it's topics 1.9 and 1.10. There are two separate videos for it on the AP College Board. This will kind of make up for the fact that 111 is huge, and I'm actually going to split that one into two separate lessons. Okay, so we're continuing with rational functions, and today we're talking about vertical asymptotes and wholes. Okay, so the big thing, we've already talked about this, about how you have to factor the denominator to find out where your asymptotes are. But we also need to talk about the fact that you can have discontinuities or wholes in a rational function if you have factors that match. Okay, that's basically what this is going to be about. Okay, so we already know why they're vertical asymptotes are in the denominator, because you can't have zero, right? And anything that makes the denominator zero is a no-no. That's a vertical asymptote that you can't have. Okay, so a whole is, again, when the factors cancel completely top to bottom, and a vertical asymptote is when they don't have something that they can cancel with. Okay, so as an example, the ones on the left both have a whole at -1 because the factors will cancel. If you take a look, right, and it's basically what this is working with. Okay, this is pretty straightforward. It just cancels out, and you'd be left with literally x plus 2 over 1, which would actually look like a linear function with the whole in the middle, or a whole at 1. Okay, this one, because this has got 2, and you can basically cancel all of the ones in the denominator out. I need you to understand that, okay? If all of the factors of something in the denominator cancel out, then it's a whole. So both of those would cancel, and you'd be left with 1 up here. So you would have a rational function with a whole at 1. Okay, so the reason this has an asymptote and not a whole at 1, okay, is because even though, we have a factor that cancels, we do, you're left with 1 in the denominator. Okay, so when the degree is bottom heavy, right, for matching factors, you're going to have an asymptote. When the degree is top heavy or they're balanced for a factor, it's going to be a whole. Okay, and that is something that you need to write down, highlight it, star it, box it, whatever, so that you remember it. Okay, so take a look at the graph. This has a whole at 1. This has a vertical asymptote at 1, right? It basically just blocks the graph from going any further. Okay. And if you take a look, when you're talking about a whole, and this actually does make a very large difference, so pay attention because we've talked about limits before. Okay, so the limit of the function as it approaches 1 from the left. Okay, so 1 from the left is coming basically here because the asymptote. 1 from the left, it's approaching 3, right? And then coming from the right, it's also approaching 3. But here's the thing. That means that the limit actually exists, right? Even though there's no actual value. So literally f of 3 would equal, not f of 3, sorry, f of 1 would equal undefined. But it does actually have a limit because it's approaching that number from both sides. Okay, so that's the difference between having a whole and having a vertical asymptote. If it's a whole, again, that point itself, the point is undefined, but you can have that limit because it is going to be approaching the same number from both sides. That works. Okay, if you have an asymptote, you can tell very specifically it's an asymptote because as the limit goes toward 1 from the left, that's this way, it's going down to negative infinity, and 1 from the right, it's going up toward positive infinity. So when you see a statement like that, where the limit to a specific number exists from both sides, right, and we're talking about a rational function, it means more than likely that there is a whole in the function at that point, especially if they tell you that the point itself is undefined. Okay, so that's basically all the notes for this unit. We're just going to do some, or for this section, we're just going to head and do some practice. Okay, so we are going to determine the holes or the vertical asymptotes or both, because it is possible to have both. Okay, so first off, we have a set of factors that match, and it's one, right? It's a balanced function as far as those factors go. There's only one of each. So there is a hole at x equals -3, right? Specifically because those factors cancel and there's no remaining stuff. Okay, and then it has a vertical asymptote at x is equal to 5. Right? Since the x plus 3 cancels to make the whole, you're only left with one vertical asymptote at x equals 5. Okay, so the next one. Okay, so remember what I said. Balanced or top-heavy means that it has an asymptote. If it's bottom-heavy, let me go back to that one so I can make sure I'm not going loopy, considering what I said before. Okay, so the reason this is, again, because it was top heavy for the factor, right? That's why it's still a whole. Okay, so balanced or bottom heavy would give you a vertical asymptote if you're looking at a set of factors. Top heavy is going to give you a whole. Okay, so there's a reason this works. So let's cancel out what we have. Okay, so I can cancel out one of my x minus 2's, and then I cancel out one of my x minus 1's. The x minus 1 is bottom heavy. It leaves it on the bottom, which means I have a vertical asymptote at x equals -1. Okay? I have a hole at x equals 2. Okay? There is an x minus 1 left over. So I want to make sure nobody, freaks out and thinks that there's an extra piece. It's not. All right, and we're going to see that again when we talk about C as far as where the holes and everything else is down here. Okay, so for this one, again, if I factor, I'm going to have x times x squared plus 4. Nothing cancels, right? There's no holes, but I do have vertical asymptotes at at 0 and at technically it would be an imaginary, but you can't have imaginary asymptotes, right? I knew if I factored it, right, I would get plus or minus 2i, but those aren't considered vertical asymptotes because they are imaginary. So you don't have to worry about x squared plus 4 ever equaling 0, right? So you just have a vertical asymptote at 0. Okay, limit statements when it comes to end behavior. Oh, no, sorry, not end behavior. We've already talked about end behavior because that's the horizontal asymptote. Okay, so as x approaches 2. Okay, so right now, nothing cancels, right? So I know for a fact that I have an asymptote, a vertical asymptote at x equals 2. Okay, so as x approaches, the limit of x, f of x, as x approaches 2 from the left, okay, is going to be, since that's an asymptote, it's going to be either positive or negative infinity, right? And then the limit of the function as x approaches 2 from the right is going to equal either, again, positive or negative infinity. So without graphing, how would we know? Well, you can plug in some numbers, right, that are bigger than 2 and less than 2. Like if I substituted in, let's say, 0, I would get, let's see, -1 times 3 is -3 over -2, which is 1.5. Okay, so that means I'm getting a positive number. If I plug in 1, let's see what happens when I plug in 1, since that's also close to 2. So like basically making a chart, since I'm getting close to 2 from the left, that's lower numbers. So 0 and 1, so that's going to be 1.5. We already know 2 does not exist. But if I substituted in 1, I would get 0 over, I would just get 0. So obviously as it's coming from the left, okay, so I'll give you a visual of that one. Okay, if 1 is at 0 and 0 is at 1.5, right, and I'm trying to go to 2, which is my vertical asymptote, you can tell that the graph is going down. Okay, it's getting less and less and less. If I put in like 1.5, it'd probably be some like ridiculously big negative number. Let's check. So if I do 1.5, I would get 0.5 times 4.5, whatever the heck that is, and then over negative 0.5. So whatever it is, I'm going to get, sorry, that's 0.5, right? Yeah, 1.5. I'm going to get some positive number divided by a negative number, so it's going to be a negative. So the graph is going down, basically like that. And on the other side, it would be going up. So again, without a calculator, you can substitute numbers in, getting closer to those limit numbers to see which way it's going. Okay, so 2 from the left is going to be negative infinity, and 2 from the right then has to be positive infinity. And again, you can prove it by just checking numbers bigger than 2. Again, if you want to make yourself a little chart and pick some numbers bigger than 2, since that's coming from the right. So how about like 3 and 4? If you substitute in 3, you're going to get 2 times 6, so 12 over 1. Okay, and it should be getting bigger and bigger and bigger. Okay, let's see. And then if I plug in 4, I'm going to get 3 times 7, right? 21 divided by 2, and that's 11.5, I think, right? No, 21, 10.5, sorry. So that means the graph would look like, okay, 3 is 12, that'd be about right here. 4 is 10.5. So literally the graph coming from the right is doing this. And again, if I put in 2.5, it should be like a lot bigger. So 2.5 minus 1 is 1.5 times, oh heck, 5.5. That's, I don't even know. Oh boy. Whatever it is, over divided by 0.5. And since I'm divided by a fraction, it's just going to get even bigger. So the graph is actually going up from that side. So again, without a calculator, you can at least get an idea of where the dots are as far as where the points are and where the graph would be going. Okay, so let's see. Let's try B. Okay, so we know for a fact that we have a whole at 2. So I'm not going to get any answers if I substitute 2 in. So this is technically my, what do you want to call it? The rest of my function, right? And I know I would have a vertical asymptote at 3. Okay, so since it's a whole at 2, we talked about this before. If it's a whole, the numbers are going to actually be defined. In this case, though, it's going to be, they cancel out, so I can just substitute 2 in for both of these. Because if I did it with these, it would just be 0. So anyway, 2 plus 4 is 6. 2 minus 3 is -1. 6 divided by -1 is -6. So it's going to be, there's an actual answer for it. So the limit of g of x as x approaches 2 from the left is going to be -6. And the limit of g of x as x approaches 2 from the right is also going to be -6. And again, this only works if there's a whole. You can plug the number in, you're going to get an answer as far as what the limit is going toward, okay? Even though the number for the graph itself wouldn't exist. When it's a asymptote, you're going to have to figure out if it's positive or negative infinity that you're going to. Okay, so this one, because it is bottom heavy, this is what we talked about, that cancels. One of those cancels, and that means I don't have a whole, I have a vertical asymptote at x equals 2. Okay, specifically because there's one left in the bottom to deal with. So since this is a vertical asymptote, that means I'm going to have to check and see whether it goes to positive or negative infinity on each side. All right, and again, all we're doing is just chucking some numbers in to see what it's going to be. So, and again, it's kind of like doing the inequalities. It's not necessarily the number that matters. The fact of if it's getting bigger, negative, or bigger, positive kind of matters. Okay, so if I substitute in some numbers that are less than 2, so let's try 0 and 1. And then we'll try 3 and 4 on the other side. Okay, so if I substitute in 0, and that's after crossing out that factor on the top, right? So 0 minus 4 is -4. over -2 times -1, which is +2. So that's -2. Substitute in 1. 1 minus 4 is -3. -3 times 1 minus 2 is -1. All over... Oh, wait, what am I doing? Brain fart. Not supposed to multiply on the top, on that second piece. Having a moment. Don't worry about me. Okay, so let's try that again. Oops. All right, so substituting in 1, 1 minus 4 is -3. On the bottom, 1 minus 2 is -1, and 1 minus 1 would be 0. Okay, so that would be undefined because that's a vertical asymptote at also x equals 1. Okay, so undefined. All right, we already know 2 is going to be a whole, so don't worry about that one. So let's try 3. 3 minus 4 is -1. 3 minus 2 is 1. 3 minus 1 is 2. So -1 over 2 is -1/2. Okay, and then 4. Okay, substitute in 4. That's just going to be 0 because that's going to be 0 on the top. Okay, so let's graph a couple of those just to give us an eyeball version of what in the heck that looks like, since we have 2 vertical asymptotes at this point. Can't get the pen to work. It's being weird. All right, actually, let's just go ahead and go to the next page. Okay, so I have a vertical asymptote at 2 and at 1. And this is the one I'm concentrating on as far as it being at 2. That's what I care about. So let's go take a look at what those numbers were. Okay, 0 was -2. 3 was -1/2. Okay, so 0 was at -2, which I'm not worried about that. It has to be between the 1 and the 2. And what did I say? 3 was... Where'd it go? 3 was -1/2 and 4 was 0. Okay, so 3 was -1/2 and 4 was 0. Okay, so that means on the right side, the graph is going down because it's getting less coming towards from the right. So that means I know that from the right, it's going towards -infinity. All right. Now, this presents an interesting challenge because it does have the 2 vertical asymptotes, and I need to know which way it's going in between them, right? So I'd have to put in like a number between, or a couple numbers between 1 and 2, as far as getting those. If I put in a couple of numbers between 1 and 2, like 1.5, 1.25, just some decimals or whatever, what I'm looking for is to see if the numbers are getting bigger going towards 2 or smaller going towards 2, right? Because I need to know if the graph is going to be going down also on this side, right? Or if it's going to be going up. And I can tell you it's going to be going up. Just because of the way the graph functions, it probably looks something like this. But again, if we were to substitute in some numbers so that you could actually check it, again, let's say 1.1, that's going to be -2.9, and -0.9 times... Oh, why do I keep doing that? I'm not supposed to hit the second number. My brain is just lost today. Okay, so let's try that again. -2.9 over, let's say, like I said, I'm doing 1.1, -0.9 times 0.1. So that's going to be negative over negative. So that's going to be a positive answer. And whatever that is, let's see. And then if I do, let's say 1.2, that's going to be -2.8 over... 1.2, -0.8 over 0.2. So it's a question of, is the number going to be getting bigger the closer I get to 2 or getting smaller? If I'm multiplying, if I'm dividing by, let's just even say these were whole numbers, that would be -16 and that would be -9. If I'm dividing by bigger numbers, I'm going to be getting a smaller answer. So that means that as I go closer to 2, I'm actually getting bigger, right? I'm dividing by a smaller number, so my numbers are getting bigger fraction, basically. So I know, hopefully you will not have to do one of those without a calculator as far as the graphing part of it, just so you can actually see it. But you get the idea that if you have a limit, right, at an asymptote, it's going to be infinity. If you have a limit at a whole, it is going to be just a number. That's the biggest goal here. Okay, so that being in your head and thinking about that, on whether or not you're going to infinity or you're going towards a whole. Okay, so we're taking a look. All right, so I'm going toward infinity at 1, basically. On the left side, I'm going toward negative infinity. On the right side, I'm going toward positive infinity. That basically means that I have an asymptote at 1. Okay, if I have an asymptote at 1, that means x minus 1 must be a factor in the denominator, period. Okay, I have a limit that is going towards a whole number at 3 from the right and from the left. Well, that means it's a whole, not an asymptote. So if it's a whole at 3, so that would be x minus 3 on the bottom and x minus 3, sorry, on the bottom and the top. And by the way, that is supposed to be 0.5, definitely not 5, because if you actually graph this thing, it's approaching 0.5, not 5. I don't know where they left the decimal off of. Okay, so, and that is one possible function that would have an asymptote at 1 and a whole, a defined, as far as the actual number, or rather the limits defined for the whole. Okay, same thing for the next one. I have a asymptote at -1, and it is going up, right, on both sides. You can see it's going up on both sides, going to 1, which means that this is not going to be a, what do you want to call it? It's not going to be something that separates by like a degree of 1, right? If you have separation by a degree of 1, then one side's going up and one side's going down. This is both sides going up, and that actually is what it tells us. So let's fill in the whole first. We know that there is a whole at -2. Okay, so that means x plus 2 must be on the bottom and the top to give me my whole. And then because the asymptote is at -1, right, and this cannot be a 1 degree separation because it's going, both sides are going up, it just means that I have to have that being a squared, so that both ends pop up at that place. Okay, so let's try the next two. This is just graphing. Okay, so the function has a whole at 1, and as x approaches 4 from the left, it increases without bound, and 4 from the right decreases without bound. Okay, so basically, since that's the asymptote, since you're increasing and decreasing without bound, that means you have an asymptote at 4. So let's put an asymptote at 4. 1, 2, 3, 4. Okay, and as it comes from the left side, it increases. So that means this side's going up and this side's going down. Okay, and then I have a whole at 1. So, okay, so like I said, this side's going up. So a whole at 1 and then going up. And then this side has to be going down. That's it. And that would be representing a graph with those limits and a whole. All right, so this one has holes at -2 and +3. Okay, so as x approaches -1, so there's my asymptote, -1. All right, so -1 and holes at -2 and +3. Okay, so there's my asymptote. And these are both decreasing. That means on both sides of this function, it's going down. So that'd be another one of those ones that has like a 2 degree difference in the denominator, just like the one we were doing before. Okay, so they're both going down, and then I have a whole at -2 and at +3. And again, wherever you want to put it is fine, as long as you are actually just drawing the graph. So if you want it up high, you don't have to have it up high, but you can. And then going down there. So that's basically what the function would look like. Okay, so like I said, short, sort of, compared to the next section that will be split into 2 pieces. And we will do some more practice on this tomorrow.